Hello, everyone. My name is Yuwen, a graduate student from Huazhong University of Science and Technology. It's my pleasure to introduce our work here. First, I will introduce the motivation of our work. Removing the brackets on 3D dental models and reconstructing the tooth surface can enable orthodontists to pre-make retainers. Patients can get retainers immediately after removing brackets, which reduces the waiting time and avoids the change of teeth position. When the retainer is lost or broken, a new one can be easily fabricated by using the archived digital model. The whole process helps to maintain the long-term stability of orthodontic treatment. However, it takes approximately 20 minutes for an orthodontist to precisely delineate brackets on a digital model. Additionally, the bracket segmentation requires a very high level of precision, otherwise it will affect the reconstruction step. An efficient and precise bracket segmentation method is crucial in orthodontic treatment. Orthodontists usually use CAD software to reconstruct the tooth surface due to the clinical applicability of its reconstructed results. However, it requires interactive manual operation, and automatic segmentation algorithms cannot be deployed to the software. To automate the entire process, a 3D mesh reconstruction algorithm is also needed. Integrating segmentation and reconstruction into a unified framework can serve as an effective tool to assist orthodontic treatment. Next, I will introduce the segmentation network BSegNet proposed in our paper. As graph-based network shows its superiority on various tasks on 3D dental models, BSegNet is based on graph neural network. In this paper, we use a 24-dimension vector as the initial input. In each local module, the first step is to construct the graph. For a given mesh cell, we calculate the feature distance between other mesh cells and select the k nearest neighbors within the range of the k plus d neighbors. We adopt the dynamic graph, which updates the neighbor information in each local module instead of the static graph. After building the graph, we construct the local feature of each cell and update the feature through the graph convolution layers. We concatenate the features of each local module and use an MLP layer to form a global high-dimension feature. Then the high-dimension global feature is concatenated with local features, forming the node-wise feature. Finally, several projection layers and one classifier layer are used to predict an n times 2 probability matrix. Then, we propose a simple yet effective projection-based method to reconstruct the tooth surface. First, we identify all the holes and extract their boundaries. Then we project the vertices of the boundary into the 2D plane. We triangulate the projected polygon without inserting new vertices. To get more uniform triangles, we use the optimal Delineating triangulation algorithm iteratively optimize the position of vertices. After the polygon triangulation, the XY coordinates are determined and a layer-by-layer procedure is employed to estimate the corresponding z-values. To avoid the vertices at the gingiva, we only use the information of the first-ring neighborhoods of the boundary vertices. Before transforming back to the original space, the extreme z-values are removed by median filtering. Then we use a rotation matrix to obtain the coordinates in the original space. We collect 80 dental mesh models in STL format from different patients. The ground truth segmentations are annotated by professional orthodontists. We compare our method with soda point cloud segmentation methods and teeth segmentation methods. BSegNet achieves the best performance. We analyze different operations and modules in the BSegNet, such as different input, aggregation operations in the graph network, and the feature constructions. The performance of the 24-dimension input is better than the 15-dimension input, which suggests the normal vectors of the vertices help the subsequent network training. Our results show that using the edge feature with the central feature is sufficient for effectively representing local regions. We also analyze the results of different aggregation operations, and the results indicate that max pooling is the most effective method for aggregation. Adopting the dynamic graph, which updates the neighbor information in each local module, the MIOU has an improvement compared to the fixed graph. Under the same network structure, using the residual connection would further improve model performance. The use of dilated KNN only brings slight performance improvement, but does not require extra computation costs. This figure displays the segmentation and tooth surface reconstruction results. In this paper, we propose a graph-based network named BSegNet for bracket segmentation on 3D dental models. Experimental results demonstrate our method significantly outperforms related state-of-the-art methods. We also propose a simple yet effective method to reconstruct the tooth surface, which can better recover the feature of the teeth. The whole framework achieves a low reconstruction error and can be used as a powerful tool to assist doctors in orthodontic diagnosis.